Yeah, now I'm recording. Perfect. All right, guys. Yeah, so yeah, for the areas under any normal curve, right? Wednesday last week we discussed. I mean, I think we did a lot of exercises, but then we tried to discuss the case of the inverse normal distribution. So let me just remind you very quickly the inverse normal distribution. So the goal was to find, I think, let me just see my notes. I think I did at least one example. Let me see. Yes, I think so. But anyway, yeah, I think I did one example. But let me just remind you the idea here. So what we are doing here is the following. So given areas or probabilities, of course, areas now correspond to probabilities, right? The area under the graph, that's exactly your probability, right? So the areas or probabilities, we want to find the corresponding value of x. We want to find the corresponding value of x. I mean, what we did before that was to, given a value of x, for example, x less than 60 or x larger than 60 or x between, for example, I don't know, 20 and 60, then we want to find, the probability that your x is, let's say your x is less than 60, or your x is larger than 60, or your x is between 60 and 80 or whatever, right? So given x, we want to find, the areas or the probabilities. Now, in this inverse normal distribution, we have the areas or we have the probabilities that are given in the problem, and then we need to find the corresponding x, right? So, and so one example, I'm just to remind you the example we discussed Wednesday last week. Just remind you the steps, and then I can go over the exercise. So, for example, let's say you want to find the value of x. The value of x. Of course, x here follows a normal distribution. So x is normally distributed. Okay. And we want to find the value of x says that, I think the example I had is, we discussed last week, is 3%, right? Says that 3% of the normal distribution lies to the right of x. Right, so so this normal distribution, the mean of this normal distribution is, I think, 40, and the standard deviation sigma is 5. Right, so in other words, so you have your, so this is the graph of your normal distribution. So I know that the mean of this normal distribution is 40 and the standard deviation is 5, right? And so the goal is to find x, right? We need to find x such that the area to the right of x is, where is it? Yeah, 3%, right? 3% of the normal distribution lies to the right of x. So the area to the right of x is 3%. Right, so this is 3%, or 0.03. So for which value of x, the area to the right of x is 0.03, right? That's the that's the goal here. That's what we want to do here. So we said the first. So to solve this problem, our first step. In the first step, we're gonna try to find the corresponding value of z, because the thing is, for the z, the variable z, that's the variable of the standard normal distribution. We have the stable number z, which gives us, the area to the left for any value of z. So what we can do as a first step is to find the corresponding value of z. Value of z, says that, the 3% of your standard normal distribution lies to the right of z. Okay. So to do that, we need to use our table. Well, first, let me just say, well, to use the table, the table gives us the area to the left, not to the right. Here, 3% or the 0.03, that's the area to the right. Now, just to remind you guys, the area to the right plus the area to the left of x, for any x, right, is actually equal to 100% or 1, right? Because that's the total area under the graph. That's always 100%. That's always equal to 1, right? So then the area to the right or to the left, so the area to the left of z, so that's just 1 or 100% minus the area to the right of z. Okay, so the area to the left, it's 1 minus area to the right. That's because the area to the left plus the area to the right is equal to 100%. It's equal to 1. So in our case, sorry. So I know that 3% or 0.03, that's the area to the right, right? This this is the area to the right. So then the area to the left of z is actually 1 minus this 3% or 0.03. Okay, so the area to the left of z is 0.97. Okay, that's the area to the left of z. And again, we need the area to the left of z because it's given, the area to the left of z, it's given by the table number 3. So next step, we can use, so we need to use the table. So we need to use now. So we use the table 3 to find z, right? And, so if you take a look to the values in the table, you start with a negative z, of course. Then the numbers, as you can see, I mean, in the if you have the table table number 3 in front of you, you can see that actually the numbers or the areas are increasing, right? So like for negative z, you start with 0.00, then it becomes 0.1, and later we have like 0.2, etc. Right? The numbers are increasing, but we need 0.97. So if you check the positive values of z, you'll see, here's your z. You have like 0.00, 0.01, you have like 0.08, 0.09, etc. And then when z is 1.8, you can see you have like 0.9641, you have like 0.9649. So we're getting close to the 0.97. That's what we want, right? The 0.97. And so then you have for 0.08, we have like I think 9699. And then for 0.09, we have like I think it's 9706. So you see the 0.97, it's actually between these two numbers, right? It's between the 9699 and 9706. Now, which one is which one is closer to 0.97? Any guess between the 9699 and 9706? Well, I mean, the difference between 0.97 and this 0.9699, it's like, you know, the difference would be like 0.0001, right? And the difference between 0.97 and 0.9706, that's like 0.0006. So of course, this one here, the 0.9699, it's closer to 0.97. So this one is closer to 0.97, right? And this number actually corresponds to 1.8, and the nearest hundredth, it's 8. So the corresponding Z is 1.88, right? So corresponding Z is 1.88. So in other words, so what we are saying is the probability that Z is less than 1.88 is the 0.97. Now, once you know your corresponding Z to this area to the right, then we can now in the next step we can find the corresponding X. So step 2, we can find corresponding X. Now, what's the relation between X and Z? So just to remind you, you know, your Z is supposed to be equal to X minus mu over sigma. So, and this is actually equivalent to X equal to sigma times Z plus mu, right? This is our change of variable. Now, if my Z is 1.88, right, then X, so I need to find X, right? So X is supposed to be equal to sigma Z plus mu. So X is equal, so what's sigma? Sigma and mu are given. So they are given, where is it? Here. You see sigma is 5, it's given, and mu it's 40, it's also given. All right, so sigma and mu, the mean and the standard deviation are given. So mu is 40 and sigma is 5. So we know sigma is 5 and mu is 40. So X would be, so the X corresponding to 1.88, that's 5 times 1.88 plus the mu plus the 40. So X is actually 49.4. So that's the corresponding X. So in other words, what we are saying here is that the area to the right of, or probability that X is larger than 49.4, that's the 3%. That's equal to 3%. And again, guys, a larger, this is larger, and larger means the area to the right. Of course, if the area to the right is 3%, the area to the left would be 1 minus 3%, and that's a 97, the 0.97 or 97%. Okay. Any questions so far, guys? I mean, so that's what we discussed actually in Wednesday last week. At the end of the lecture, and I think we had, let me see, one exercise or two. I'm not sure. Let me see my notes. Yeah, there's one exercise. Well, I'm gonna just try to solve at least one exercise because I think we don't really have time. I need to cover section 7.5. So let me just remind you of this exercise. So we said the time. So this is like a real life problem, right? So suppose the time to complete a test is normally distributed. It follows a normal distribution. With mean equal to, let's say, 40 minutes, and standard deviation sigma is 5 minutes. So the question is the following. So after how many minutes, after how many minutes can we expect all but 3% of the tests to be completed? Completed. Okay. So yes. So let me explain this. So first, we have the time to complete the test is normally distributed. So your variable x is actually the time to complete the test, right? And the variable x follows a normal distribution, right? So the variable x here. So the time to complete the test is normal distribution. It's normally distributed. So the variable x, that's the time to complete the test. X, that's the time to complete a test, and it actually follows a normal distribution to complete the test. It follows the normal distribution, and we know that the normal distribution, the mean of the normal distribution is 40, and the standard deviation is sigma. Right? Now the question is, after how many minutes can we expect all but 3% of tests to be completed? So so we have you have the graph of your normal distribution here, and you have your x. Okay. And the x, again, that's the time to complete the test. To complete a test. So let's say x is 50. I'm gonna just take some random value here, okay? Just to give you like some numerical example. So 50 here is just a random value, right? So let's say x is 50 minutes. Okay. So what does represent the area to the left of x? Again, that's the time to complete the test, right? So the area to the left, that's the probability, right? Or the percentage of tests, right? The percentage of tests that can be completed before 50 minutes or in 50 minutes, okay? So you see this area to the left, this is the percentage or the probability. This is a percentage of, let's say, tests completed in, let's say, less than 50 minutes, right? Because X, again, the X, your variable, that's the time to complete the test, right? So the area to the left, that's the percentage of tests completed in less than 50 minutes. And the area to the right, that's the percentage of tests not completed after 50 minutes. So this is the area to the right, that's the percentage of tests not completed not completed in 50 minutes. Okay, so you probably need more than 50 minutes to complete your test. Now, what we want is, so how many minutes can you expect all but 3% of tests to be complete? So the 3%, that's the percentage of tests not complete, right? So all but, we expect all but 3% of tests to be completed. So because of the but here, by 3%, that's means that the 3%, that's the percentage of tests not completed, right? So in our example, the 3%, that's the percentage of tests not completed after X minutes, right? And the variable X is unknown. And that's actually what we need to find, the X, right? This is the unknown. Does this make sense to you guys? So again, you need to understand of course, the problem here. So usually, I mean, before that, the kind of problems we had is like, what's the percentage or probability that you finish your test, before 40 minutes, or what's the probability or the percentage, or what's the probability to finish your test like between 30 and 50 minutes, right? So the time to complete the test, it's given, right? The 30 minutes or the 50 minutes, it's given. But here, the time to complete the test, it's not given, right? What's given here is the percentage of tests not completed. So we need to find the corresponding X. We need to find the corresponding time to complete the test. Okay, so what we need to do here is we need to find the corresponding, find the value of X says that 3% of the normal distribution lies to the right of X. Okay, and that's exactly what we did in the, in the previous example. As a first step, we said we need to find the corresponding Z. Find the corresponding Z, and then corresponding Z, and then we said this is 3%. That's the area to the. This is the area to the right. So the area to the left, that will be 1 minus 3%. So that's 97%. Okay, and so we said the corresponding z is 1.88, right? That's from the table number 3, right? And then, next step we need to find the corresponding x. Find corresponding x, which is x. So then we said x is sigma times z plus mu. So x is sigma, the standard deviation and the mean are given, right, in this problem. We said it's normally distributed with mean 40 and sigma is 5. So sigma is 5, and so 5 times, again, 1.88 plus 40. So x is actually 49.4, I think, minutes. Okay. So, I mean, the conclusion here, so what we are saying here is that after 49.4 minutes, so after 49.4 minutes, we can expect all but 3% of the tests to be completed. Okay. Yeah, so so this is like as I said, it's like a real life problem where you have given the area or the probability, right? This 3%, it's given, and that's the area to the right of your x, right? So then you need to find the corresponding x, which is again the x. That's the time to complete the test. Okay. Any question, guys? So again, this is an exercise from Wednesday last week. I think I didn't have time to, explain this very well. So yeah, so that's so I guess now if there's no question, guys, I can move to the section 7.5. The central limit theorem, which is a very important, as I said, very important theorem. And we'll see why this normal distribution is so important in statistics. Okay, well, I guess there are no questions. So yeah, so this is section 7.5, central limit theorem. So as I said, this is not included in the test, right? The 7.5, this is not in the second test. It's going to be, of course, in the final, but not in the test. Juliana, you want to see? Oh, the previous page? Okay, yeah, sure. Oops. The bottom? Okay. Is this okay? Okay. Well, yeah, so this 7.5 is not in the second test, so it's going to be in the final. And probably, as I said, I'm going to assign last homework this Wednesday, and you're going to have a couple of exercises about this 7.5, so I guess, you're going to have some time to practice a little bit before the final. Are you done?
Thank you.
Jordana? Okay, sure. So yeah, I'm gonna, you know what? I'm gonna just state the theorem. I'm gonna try to explain the theorem and what does the theorem say, and then of course we'll have some examples. So central limit theorem. So what's this central limit theorem? Well, so actually we're going to have two theorems in this section. In the first theorem, our variable is normally distributed. It follows a normal distribution. And the second theorem, the variable x, it's not necessarily normally distributed. Okay. But anyway, you'll see why this normal distribution is so important. So yeah, so the first theorem, theorem 1. So this is for a normal distribution. This is for a normal distribution. So you have your x, random variable x with which follows a normal distribution, right? So let x be a random variable which follows a normal distribution. So x here as a variable of a normal distribution with the mean mu and standard deviation sigma, with mean equal to mu and standard deviation equal to sigma. Okay. Now, okay, so we have this variable x follows a normal distribution as usual. A mean is mu and standard deviation is sigma. Now what I'm gonna do, I'm gonna take x bar, the sample mean. So let x bar, so this is x bar. So this is the sample mean corresponding to random samples of size n. Of size n. Right, so the x bar, it's just the sample mean corresponding to samples of size n. Okay. So this x bar is taken from the x distribution. Taken from the x distribution. Okay. Then we have the following. The x bar distribution is actually normal. So first, so 1. The distribution of x bar, with the x bar distribution is normal. Okay. The mean of the x bar distribution is actually the mean of this X bar of this X bar distribution is it's mu. Okay, and then the third point is that the standard deviation of this X bar distribution is actually the standard deviation of the X bar distribution. So the X bar distribution is, sorry, standard deviation, of course. Oops. The standard deviation. So the standard deviation of the X bar distribution is actually sigma over square root of n. Okay. So what the theorem is saying here is that you have this this x which is a variable which follows a normal distribution, etc., right? And then you have the x bar. The x bar, that's the sample mean, corresponding to random samples of size n. The size of the samples are fixed, right? So we have, let's say, 100, 100 samples of size n. Okay, and of course each sample has an x bar, has an average, right? So then, because each each sample has like an x bar, so you have like an x bar distribution. And so the theorem is actually is saying the following. So the idea is that so what the theorem says is the following. So the idea is that the x bar, the sample mean, x bar distribution is actually normal. It's normal. Okay, and the mean of the distribution of x bar is the same as the mean of your variable x, but then your standard deviation of x bar, okay, it's actually standard deviation of x over square root of n. Okay. So let me give you a concrete example. Okay, so then you see the difference between the x and the x bar. So here's an example. So let's say x is the length of a single fish. X, that's your variable. So x is the length of a single fish, just one fish, right? Of a single fish, taken at random. Okay, and let's say this x, this length of a single fish, has a normal distribution, right? X has a normal distribution. And so, for example, distribution, let's say, I'm just going to take just a random values here. So let's say mu is 10.2 inches, for example, and sigma standard deviation of this normal distribution is 1.4 inches. All right. So for example, we can try to find, so we can, for example, we can try to find the probability. So what's the probability that a single fish taken at random, of course, is between, let's say, between 8 and 12 inches long, for example. Okay. Again, X represent the length of a single fish taken at random, right? You know the mean, you know the sigma, and then you want to find, for example, probability that a single fish taken at random is between 8 to 12 inch long. Okay. So what we do in this case, this is, so you need your X. The X is the length of the fish, right? The X is the length of a single fish, just one fish, right? And you want a probability that the length of the single fish is between 8 and 12. So you need your X, because X, that's the length of the fish, right? You need your X to be between 8 and 12, right? So we need to, so what we want to do here, we want to find the probability that X is between 8 and 12, right? X is, because X again is the length of a single fish, and we want to find the probability that the length of the single fish is between 8 and 12. That's the probability that X is between 8 and 12, right? This is the probability that X is between 8 and 12. And actually, we know how to do that, right? This is a section we discussed this in the section 7.3, the last section. So we said, first, as a step one, we need to convert, the X to Z. So just to remind you the steps. So we said, like, as a step one, we need to convert X to Z. So that's, just to remind you, your Z is supposed to be the Z, that's a variable of the standard normal distribution, of course. So Z is X minus mu over sigma, right? So this is the probability that your Z, now you convert 8 to some value of Z. So that's 8 minus 8 minus mu over sigma, and mu is 10.2 and sigma is 1.4. So this is 8 minus 10.2 over sigma, which is 1.4. Right? Now we need to convert the 12 to some value of Z. This is the 12, that's a value of X, right? The 12, that's a value of X. So we need to convert this value of X, the 12, to some value of Z. Well, to convert to some value of Z, we need to subtract the mu, the mean, which is again 10.2, or the sigma, which is 1.4. Right? That's what we did in the in the section in the previous section 7.3. And so then you have this probability. So 8 minus 10.2, that's like minus 2.2 over 1.4, less than Z, less 12 minus 10.2. Sorry, over, so 12 minus 10.2, that's 1.8 over 1.4. Right, then you divide. So this is probability minus 2.2 over 1.4. This is minus, I think, 1.57. Right, less than z, less 1.8 over 1.4. I think it's, let me check my notes, it's 1.29. All right. So now the probability that z is between two numbers, we said this is probability, this is equal, so this is equal to the probability that z is to the left of the second number here, minus the probability that z is to the left of the first number, the negative 1.57, right? Just to remind you, so you have your graph. You have your 1.29, and here it's the negative 1.57, right? And you want to find, the probability that z is between these two numbers, which is the area of this region, right? Between these two numbers. Okay, now what's the area between these two numbers? Well, so what we do, and what we said in section 7.3, so we take the area to the left of the 1.29, right? This, this area here, represented by this green arrow. That's the area to the left of 1.29. And we subtract the area to the left of the negative 1.57, right? This area here. Right. So as you can see, the difference is exactly between the areas to the left. The difference is exactly this, right? And that's exactly what we want, right? It's the area between the two numbers, right? The difference would be the area between the two numbers. So yeah, so what I'm saying here is that, so this is always, so when you're looking for probability that z is between two numbers, that's always probability that z is less than the second number, the 1.29, minus probability that z is less than the first one, the negative 1.57. And now I can use my table, right? Because my table number 3 gives us the the areas to the left, right? So we can use table number 3 here. Right. So for this probability that z is less than 1.29, so nearest tenth is 1.2, nearest hundredth is 0.09. And if you check your table, well, I guess I can share my screen too. But I mean, I hope you have your table number 3 in front of you. So this is probability that z is less than 1.29. This is actually 0.9015. Okay, minus. And the second one, nearest tenth, it's negative 1.5, and nearest hundredth is 0.07. Right, so, but just be careful, this is positive here, and this one is negative, right? So the first page of the table, that's for negative z. Second page is for positive z. Anyway, so for this probability that z is less than negative 1.57, it's 0.0582, I think, right? And so the difference is 0.8433, or in other words, take the 2 digits after the decimal point, so that's 84.33%. Okay. Does this make sense to you guys? Is there any question? Please, I mean, don't be shy. I mean, I'm here to answer, of course, your questions. So, but again, this is what we did Wednesday last week, right? And I think we had a lot of exercises about this. So there's nothing new here. It's just from the previous section, right? So what's new is the next question, right? So next question is, what's the probability that the mean length X bar of 5 fish taken at random? So let me just say, so here, let me just write it down here. So in the A, so in A, there's nothing new. This is, so let me just write down the remark. So this question A, so A, there's nothing new in A. There's so A was discussed in section 7.3. Okay, so nothing new here. All right. Now, next question, and this is where we're gonna use our theorem. So B, what's the probability that the mean length X bar of 5 fish of 5 fish, right, taken at random, of course, is between, taken at random, of course, is between 8 to 12. Eight to 12 inches long. So you see the difference between A and B. So in A, again, the X is the length of a single fish. And in A, we try to find the probability that the length of a single fish is between 8 and 12, right? So we take just one fish, right? Just one fish. And you want to find the probability that the length of this single fish is between 8 and 12, right? It's just one fish. Now, in B, we have a sample of 5 fish, right? You have this 5 fish, not just one, not a single fish, it's 5 fish, right? So this is, so we have 5 fish. So this is like, so we have like a sample of 5 fish. That's a sample of 5 fish. Okay, so we have 5 fish, and of course you can compute the the mean, the average length of the 5 fish, right? That's the X bar. X bar, that's the average or length average. This X bar, that's the average length of the 5 fish. So what the theorem says, our theorem says that this X bar, the mean of the sample actually follows a normal distribution too. Okay, so if you have a normal distribution, then the mean of a random sample also follows a normal distribution, and the mean of this normal distribution of X bar is actually, so what the theorem says, so the theorem says the following. The theorem says the following. So our theorem 1 says that, so this mean length, so X bar, this is the average length, right? This is normally distributed, okay? Is normally distributed. Okay, and the mean of this normal distribution, right? Because it's so we have a normal distribution, right? And the mean of this normal distribution is the mean of the the original variable x. Okay, it's the mean of x. The mean of x is, if you come back to the problem here, so the mean of x is this, mu is 10.2. That's the mean of x. So what we are saying is, so the mean of the x bar is, it's just the mean of x. So that's 10.2 inches, right? And then the standard deviation of this, the x bar, it's actually standard deviation of x over square root of n, right? So in our example, the standard deviation of x, the sigma. So we said sigma is, now here's our sigma. Sigma is, as you can see, sigma is 1.4. So sigma is, it's 1.4 divided by the square root of n. So what's n here? N is the size of the sample, right? N, that's the size of the sample. And in our problem, the sample, we have the 5 fish, right? We have 5 fish, right? And we are interested in the mean, x bar of the 5 fish. So the sample, the size of the sample is 5, right? Because we have 5 fish. So yeah, so this is 5. Size of the sample is 5 because we have 5 fish. Because we have a sample of 5 fish. We have a sample of 5 fish. Okay. So yeah, so this is actually 1.4 over square root of 5. This is actually equal to 0.63. So the standard deviation of x bar is 63. So what we need to do here, guys, we need to find the probability that the mean of this 5 fish taken at random is between 8 to 12 inch long, right? So we need the x bar, the mean of the 5 fish, the mean length of the 5 fish is actually between 8 and 12, right? So we need the mean of the 5 fish. So let me write it in words here. So we need the probability that, where we want so we want to find the probability that the mean length of the 5 fish is between 8 and 12. 5 fish is between 8 and 12. So in other words, we need to find the probability that x bar, the mean length of the 5 fish is between 8 and 12. Right? So this is very different from A. In the question A, it's the probability that x is between 8 and 12. X is, that's the length of a single fish, just one fish, right? In B, we are interested in the mean of our sample of 5 fish, right? And we want to find the probability that the mean of the mean length of the 5 fish is between 8 and 12. So we need the x bar, the mean, to be between 8 and 12. Okay. So in the A, it's just one single fish. That's why it's just x, between 8 and 12. Here, it's the mean length of 5 fish. So that's why we are using x bar, the mean of the sample, right? Remember the notation for x bar? That's the mean of a sample, right? So we need the mean of the sample of the 5 fish between 8 and 12. Does this make sense to you guys? I mean, at least do you see the difference between A and B, right? So A is just one single fish. You need the length of the single fish to be between 8 and 12. Here in B, it's not one single fish. It's the mean length of 5 fish. Okay. All right. So yeah, so that's the difference, and that's so in B, we are trying to apply our theorem, and so we are saying, so this X bar follows a normal distribution, and so as usual, when we have a normal distribution, so this is exactly, so we're gonna do exactly the same thing as we did in the A. You know, in A, you have your X, it follows the normal distribution, so we need to convert your X to Z, X minus mu over sigma, etc. And then use the table, and you can find your answer. So here, X bar, it's also the same thing. So X bar follows the normal distribution. So as a first step, I'm gonna convert X bar to Z. Okay, so that's probability. So you have your X bar. So we need to convert 8 first. That's a value of X bar to a value of Z, right? So when you convert, so your Z is supposed to be equal to, your X, your variable, minus the mean. So X bar has the same mean as X. So it's just X bar minus mu over the standard deviation of the distribution of X bar. Now, the distribution of X bar, the standard deviation, it's not the same as the standard deviation of X. So the standard deviation of X bar is actually sigma over square root of n. Okay. So, so if you want to convert this 8, so it's 8 minus the mean, which is, so the mean, it's just the 10.2, right? It's just the same as the mean of x, that's the 10.2. So it's 8 minus 10.2 over, now it's not divided by sigma, it's actually divided by it's divided by sigma over square root of n. All right, so it's divided by this number here, sigma over square root of n. That's the standard deviation of the X bar distribution, which is actually 0.63, right? So we need to divide by 0.63. So it's 0.63, right? The 12, the same thing. So so it's 12 minus 10.2, the mean of the X bar distribution, which is the same as the mean of mu of X, and then over again the standard deviation of the X bar distribution, right, which is a sigma over square root of n, and we said that would be equal to 0.63. So yeah, and then so this is probability that X is X bar. So 8 minus 10.2, that's negative 2.2 over 0.63, and 12, minus 10.2, that's 1.8 over 0.63. Right, so this is probability that, so your X bar, so negative 2.2 over 0.63, it's actually negative 3.49, and 1.8 over 0.63 is 2.86. Okay. So, sorry, this is, of course, this is Z here. I'm sorry. Should be Z here. Oops. Should be Z. All right, we converted X bar to Z, so this should be Z, sorry. This is, of course, Z. All right, because we converted X bar to Z. Now, this is just the difference. So your Z, probably that your Z is between these two numbers. That's probably that Z is less than 2.86 minus probability that Z is less than negative 3.49. Now we can use the table. Okay, so probability that Z is less than 2.86. So nearest tenth is 2.8, nearest hundredth is 0.06. So that's actually from the table, that will be 0.9979, right, for 2.86. Now for negative 3.49, actually the smallest the smallest value in the table, it's negative 3.48. You know, if you check your table and you check negative values of Z, the smallest value of Z is actually negative 3.48. But you know, we said we treat any value smaller than negative 3.48 as so the area to the left would be just 0. So this is minus, you know, 0, just it's just 0. Okay, so that's equal to you know, if you check your table, oh yeah, we do have a negative, actually. The smallest value actually is negative 3.49, right? So it's 0.0002, right? This is a very, very small number, very close to 0. Yeah, so then the difference, of course, is 0.997. Right? In other words, this is 99.77%. Right? So then it's negative 3.49 is actually the smallest, you know, value in the table. But anyway, yeah. So that's that would be the answer. But again, as you can see, the difference between the A and B. So in A, we are interested in the probability that X, that's the length of a single fish between 8 and 12. In B, and that's where we use our new theorem, we are interested in the probability that the mean length of a 5 fish is between 8 and 12. Okay. So let's have an exercise, another exercise, no problem. Exercise. Give you some time to think about this exercise. I'm gonna just take an exercise from the textbook. So this is actually exercise 14, page. This is exercise 14, page 344 in the textbook. Anyway, so it says the following. So the heights of 18-year-old men are normally distributed. Okay, with mean U. So mean is 68 inches. And standard deviation sigma is actually 3 inches. All right, so A, what's the probability that an 18-year-old man selected at random man selected at random, of course, is between 67 and 69 inches tall. Right. So this is just a single, just one 18-year-old man, just a single man. Now in B, I'm gonna take a sample. I'm gonna take a sample of 9 if random sample of 9 18-year-old men is selected. So what's the probability that the mean height is between 67 and 69? What's the probability that the mean height x bar is between 67 and 69 inches? Okay. All right, I'll give you a couple of minutes to think about this. So as you can see here, the difference between A and B. In A, we select at random just one 18-year-old man, right? So, and then in B, we have a sample of 9 18-year-old men. So let me just say, guys, I mean, for A, this is, again, this was discussed in section 7.3. So we are looking for the probability that X is between 67 and 69, right? And in B, we are looking for the probability that X bar, the mean of this sample of 9 18-year-old men, is between 67 and 69. Well, I guess we can we can solve this together. So for A, so as I said, so for A, we need the probability that that an 18-year-old man, so it's just a single man, right? Just one man selected at random, is between 67 and 69, right? That's, so we need our X, probability that X is between 67 and 69, right? Because again, that's just a one single man, an 18-year-old man, right? So just one man, right? This is one, just, so here we have one, just one man. Okay. And again, X, that's the height, of course. And you need the height to be between 67 inches and 69 inches, right? So then, as usual, so as the first step, we need to convert this to Z. Convert X to Z. All right, so that's probably that, so your Z is between, so 67, so X, just to remind the relation between Z and X, so Z is actually X minus mu over sigma, right? So it's 67 minus mu, mu is 68, right? And sigma is 3 inches. So that's 67 minus 68 over sigma over 3, right? And on the other side, it's 69 minus 68 over 3, right? So it's X minus mu over sigma. So so that's a probability that your Z is between, so 67 minus 68, it's -1. So -1 or minus 1/3. So -1 over 3 Z. This is Z, of course. And this is on the right side, you have 69 minus 68. That's 1 over 3. Right? In other words, this is probably that, -1 over 3, of course, that's just a negative 0.33. And this is positive 0.33. Right? So then, again, Z between two numbers. So then it's probability that Z is less than the second number. So the area to the left of 0.33 minus the area to the left of negative 0.33. Okay, so then we can use the table, our table number 3 here. So Z is less than 0.33. If you check the table, let me see the table. So this is positive. So nearest tenth is 0.3, and nearest hundredth it's 0.03. So that's 62. So 0.6293 minus. Now negative 0.33. So that's z is negative. So that's the first page of the table. So nearest tenth is minus 0.3. And the nearest hundredth is 0.03. So that's 0.3707. 3707. And so the answer, so the difference is actually 0.2586. Okay. Which is, sorry, oh yeah, so that's correct. So yeah, so 2586. So which is, oops, sorry. Sorry about that. Yeah, so that's equal to 25.86%. So the probability that that the height of one 18-year-old man between 67 and 69 inches is actually 25.86%. Now in B, so in B we have a sample of 9 18-year-old men, right? So the size of the sample in B is 9, right? Because as you can see, we have 9 18-year-old men, right? So we have a sample of size 9. So the size of the sample is 9. So in B, we have a sample of size 9, right? Because we have 9 18-year-old men. So the size of the sample is 9, so n is 9. Okay. Now we are looking for the probability that the mean height x bar, so that the average height of the 9 18-year-old men is between 67 and 69, right? We need the x bar, the mean of the sample, to be between 67 and 69. So we need the probability that x is x bar, not x, but x bar. So we need the probability that x bar between 67 and 69. Right. So as I said, but by our theorem, we know this x bar, this the mean of the sample mean, it follows a normal distribution. So if it follows the normal distribution, we can always, convert the variable to the variable z, and then use the table number 3, right, etc. But first, what's the mean of this normal distribution, the normal distribution of x bar? So mu of x bar is just the same as the mu of x, which is the mean of x, it's 68, right? That's the mean, the mu of x. The mu of x is 68. That's the mean of the population, right? The mu of x is 68, and its sigma is 3. So now for the sample mean, the mu is, as I said, it's the same as the mu of x. So it's 68 inches, right? But then the standard deviation of x bar, of the mean, it's actually a standard deviation of x over the square root of the size of the sample. So the sigma here is 3 inches. So sigma is 3 over square root of n, and the size of the sample n, we have 9, a sample of 9 18-year-old men. So it's a square root of 9, right? So a square root of 9, 3 times 3 is 9, right? So then square root of 9 is 3, right? So this is just the 3 over 3, so which is 1 inch. Okay, so the mean of x bar is, or the mu of x bar is 68, and the standard deviation of x bar is 1 inch. All right, so now we can convert this x bar to z. Once we have the mu and the sigma, we can convert. So 67 x bar 69, that's what we want to compute. So as a first step, we need to convert this to z. So step 1. So we need to convert to z, right? So this is probability that your z, sorry, now, because we converted x bar to z, so now it's z instead of x bar. 67, we convert this 67, that's supposed to be a value of x bar. Now we convert to some value of z. So that's 67 minus the mean. The mean is, or mu, minus mu. Mu is 68 over the standard deviation of x bar. Standard deviation of x bar, it's actually 1. So over 1. And on the other side, you have 69 plus, minus 68 over, again, over 1. Right, the standard deviation of x bar. So yeah, so this is actually probability that your z is between, so this is 67 minus 68, it's a negative 1 over 1. 69 minus 68, it's 1 over 1. So this is just the probability that z between negative 1 and positive 1. Okay, and so we can use now our table. Well, before the table, let me just say, so this is probability that z is between two numbers. So that's probability that z is to the left of the second number, that's 1, minus probability that z is to the left of the second number, which is negative 1. Okay, and now I can use my table. So probability that z is less than 1, so 1 is positive. So nearest 10th is 1.0, and nearest 100th is just 0.00. So that's 0.8413. Now for negative 1, it's nearest 10th is negative 1.0. Nearest 100th, of course, is just 0.00. So it's minus 0.1587. 0.1587. Okay, and then so the difference is actually 0.6826, which is 68.26%. Okay. Any question, guys? Yeah, so anyway, so this is just an application of our theorem. So next, how much time left? Okay. Now, as I said, so in this section, actually, we have two theorems. So in the first theorem, so in this first theorem, the x, our x, the variable x, it follows a normal distribution, right? I said, remember I said x, so this is for a normal distribution, right? My x, a random variable which follows a normal distribution, right? Now, the second theorem, our x doesn't follow necessarily a normal distribution. So in the theorem number 2, so this is now theorem number 2. If you have a distribution, so this is theorem number 2, and this is why actually this theorem explains why the normal distribution is very important. So this is this is for any. So theorem 1 was for a normal distribution. This is for any distribution, any probability distribution. It doesn't have to be a normal distribution, for any probability distribution. Okay, so that's why this theorem is very very strong. So it's for any. Okay, it's not necessarily a normal distribution. So it's for any probability distribution. So the theorem says the following. So if x follows any probability distribution, as I said, it doesn't have to be a normal probability distribution. Any probability distribution with mean mu and standard deviation sigma. Okay, then the sample mean x bar based on a random sample, on a random sample of size n, will actually approach a normal distribution. So in other words, so if your x follows any probability distribution, again, it doesn't have to be a normal distribution, and that's why normal distribution actually are very, very important. Then the sample mean actually is going to approach a normal distribution as n grows to infinity, or as n gets very large. So we'll approach a normal distribution with mean, same mean, and standard deviation sigma which is equal to sigma over square root of n. So it's going to approach a normal distribution as n grows to infinity. As n grows to infinity. Okay, as the size of the sample gets large. So in other words, so interpretation of this theorem. So what does the theorem says is the following. So interpretation. So regardless of the type of the distribution, x as a, so regardless of the type of the distribution, that doesn't have to be a normal distribution. Of the type of the distribution, type of distribution of x, the x bar the sample mean, the X bar, the sample mean will approach the X bar, the sample mean, right? Will approach or can be approximated by a normal distribution, will approach a normal distribution, normal distribution. Okay. And actually, as a convention, you know, because here we're saying, well, as n grows to infinity, we're going to approach this normal distribution. So as a convention, we're going to agree that if the size of the sample is, let's say, larger than 30, we can just use this the central limit theorem. We can use this theorem. Okay, so as so this is a convention. Let's say if the size of the sample. So let's agree that if let's say n is 30, okay, we can use you know, the central limit theorem. You can use the theorem. Okay. So let me give an example. All right. So an example, numerical example. So let's say x represent. So x, this is the dollar amount spent on spent, let's say, in the 10-minute shopping interval. Okay, and so let's say this x. So the probability distribution of x, probability distribution of x, probability distribution of x. It's actually not a normal distribution, but it has, let's say, has mean mu. Let's say mean mu equal to 20. Let's say $20, and standard deviation sigma equal to $7. Right. So again, x is the money spent in 10-minute shopping interval. And let's say this is, it's not, x doesn't follow a normal distribution, but we know that the mean of x is actually 20, and the standard deviation is sigma, right? So the question is the following. So let's say you have a random sample of 100 customers. Okay, a random sample of 100 customers. Okay. Now, so what's the probability that, let's say, the x, so what's the probability that your x bar the x bar, that what's the probability that x bar, okay, so the x bar, that's the sample mean. So that's the mean or the average the money spent by the 100 customers, right? We have 100 customers. They spend some money in a 10-minute shopping interval. And so the X bar, that will be the mean, right? Of that's the sample mean of, so this is just the average. It's just the average amount spent by the average amount spent by the 100 customers. Okay. So what's the probability that this X bar is between, let's say, 18 and $22 is between 18 and 22. So what's the probability that the average amounts spent by 100 customers is between $18 and $22, right? So as I said, so the X, the X is, it doesn't follow a normal distribution, right? So again, the X, that's the dollar amount spent in a 10-minute shopping interval. It doesn't follow a normal distribution, but we know that its mean is 20 and standard deviation is sigma. Now we have a sample of 100 customers. Okay, this is our sample. We have 100 customers, right? So the size of the sample is 100, right? Because we have 100 customers. So the size, so this is a discussion. So the size of the sample is 100, right? Because we have 100 customers. Now 100 is, it's larger than 30, right? Because that's our convention, right? If it's if the size of the sample is larger than 30, then we can just use our theorem. So this 100, of course, is larger than 30. This is larger than 30, which is our convention. So we can use our theorem. We can use our theorem. So what does it say, the theorem? Well, it says that this sample mean, or the average amount spent by the 100 customers, actually follows a normal distribution. So this X bar, the average amount spent by the 100 customers. So the X bar actually follows a normal. So then follows a normal distribution. And the mean of this X bar is going to be just the mean of the variable X. So the mean of the variable X, as you can see, is $20, right? So this is $20. And the sigma, the standard deviation of X bar, it's just sigma over square root of n. So sigma is 7. So it's $7 over square root of n. N is the size of the sample, right? The n, that's the size of the sample. We have 100 customers, right? So the size of the sample is 100. So 7 over 100. Square root of 100 is actually 10, right? Because 10 times 10 is 100, right? So then square root of 100 is 10. All right, so 7 over 10, that's 0.7 or 70 cents. Okay, 0.7. This is 0.7. Okay, so now we want the probability that X bar is between 18 and 22, right? So we need to find probability that X bar is between 18 and 22, right? So then, so as usual, as a first step, we convert to Z. So step one, convert to Z. So now it's instead of X, we have X bar, we have Z. Now convert 18 to some value of Z, sorry. So that's 18 minus mu, the mu of, or the mean of the X bar. So that's the same as the mean of X, that's 20. So 18 minus 20 over the standard deviation of X bar, which is 0.7. 0.7, right? And here's same for 22. So it's 22 minus 20 over 0.7. So this is actually equal to, so it's probability that, so you have your Z. So this is -2 over 0.7, and this is +2 between over 0.7, right? So that's probability that your Z is between, so -2 over 0.7, I think it's negative 2.857, I think, and 2 over 2 over 0.7, that's +2.857. Okay, and now, so again, this is Z between two numbers, so that's probability that Z less than the second number, the largest number, which is the +2.857, minus Z less than the first one, the -2.857. Okay. Now we can use the table. This is from the table number 3. Right. And yeah, so for 2.857, I guess the nearest 10th is 2.8, nearest 100th is the 0.05. So I think that would be 0. So this is 0.9979 minus now negative, this is -2.85, right? So here Z is negative, it's -2.85. So nearest 10th is -2.8, nearest 10th, I think it's 0.05. So I think this is 0.0021. So then the difference is 0.9958. In other words, that's 99.58%. So what we are saying is that there is 99.58% chance that the mean or the average amount spent by 100 customers is actually in a 10 minutes interval, shopping interval, is between actually 18 and $22. Okay. Any question, guys? So again, the idea of this section is to compute the the probability of x bar, right? The sample mean. And so what we are saying here is that in general, if you have a variable x, then the sample mean x bar actually follows a normal distribution. Okay, even if your x is not a normal distribution, but the x bar is going to actually follows a normal distribution as the size of the sample gets large, right? So as the size of the sample gets large, you can approximate your the distribution of x bar by a normal distribution. But then the normal distribution of this x bar, the mean is the same as the mean of x. But then just be careful. The standard deviation of x bar, it's not exactly equal to the standard deviation of x, right? It's the standard deviation of x over the square root of the size of the sample, the square root of n. All right. You want to see the? Oh yeah, sorry, Juliana. Sure, thank you. Here. Sure. So we have like 15 minutes left, and actually we are done with this section. I mean, I covered the two theorems, the main two theorems in this section. I mean, we can do more exercises, I guess, in the last 15 minutes. Probably just one more exercise. I don't know if you're going to have time to cover, to solve the exercise, but I can always, write down exercise, give you some time to think about it. And then, but I think on Wednesday, so on Wednesday, I'm going to probably cover section 8, 8.1, 8.2 from chapter chapter 8, right? And I don't think I'm gonna have time to to cover anything from chapter 9, right? So that's that's unfortunate, but yeah, it's just because I guess it's with the online teaching, I guess it takes more time to explain probably things. But anyway, so yeah, let's do one more exercise. So in the last 15 minutes, let me at least write down one more exercise. So this would be exercise number, example. We had an example. Okay, so another example or exercise. So let me just erase this line here. So yeah, so exercise or example number 2. Here we can take an exercise from, I guess, from the textbook. So okay, so let's say okay, we can do the number 13, exercise 13, page 344. So it says the following. So coal is carried from a mine in West Virginia, okay, to a power plant in New York. So it's carried in hopper cars. Sorry, in hopper cars on a long train. Okay. So we can put 75 tons of coal in each car. So we can put 75 tons of coal into each car, let's say. So let's say the actual weights of coal loaded in each car. So the actual weights of coal loaded into each car are normally distributed. With mean 75, tons, and sigma standard deviation 0.8 tons or ton. So A, first, so what's the probability that one car chosen at random will have less than 74.5 tons of coal? So what's the probability that one car chosen at random will have less than 74.5 tons of coal? Okay. B, what's the probability that 20 cars chosen at random would have a mean load weight X bar of less than 74.5 tons of coal? So what's the probability that the 20 cars of chosen at random would have a mean of load load weight X bar of less than 74.5 sorry, yeah, 74.5 tons of coal. Juliana, what letter is after the weights off? This is off. You mean this one here? So weights of coal. Does this answer your question, right? That's exactly what that's exactly your question, right? That's the letter after. Okay, so that's off. OF. So let me just say, guys, here the difference between A and B. In A, that's just one car, right? Chosen at random, one car. Chosen at random will have less than 74.5 tons of coal, right? So of course the X, the variable X in this problem. So it says the actual weights of coal loaded into each car are normally distributed. Okay, so it means that the weight of the coal loaded into each car follows the normal distribution, So the variable x here, that's the weight, right? That's the weight of the coal loaded into each car. So that's your x, right? So let me just say here. So the x, the variable x, that's the weight of the coal loaded in each into each car, loaded into each car, right? Now this x bar, you see this x bar, where is it? This x bar, that's the mean load weight of this 20 cars. Okay, so this the x bar, that's the mean load weight of coal loaded into 20 cars. Okay. So let me just say, guys, on the last 4 minutes, let me just say, so in A, we need to find the probability that one car, just one single car. Okay, we don't have a sample here. It's just one single car chosen at random will have less than 74.5 tons of coal, right? So that's the probability that your x is less. Again, the x is the weight of the coal loaded in each car, right? So your x is less than, this is less than 74.5. Okay, so that's what we are looking for here. And of course we can, because your x follows the normal distribution here, we can use as a first step, we can convert x to z and then use the table, etc. Now for B, in B we are interested in the mean load weight x bar of of 20 cars, right? So we have a sample here. In B we have a sample of size 20, because we have 20 cars. So, and we need this mean load weight to be less than 74.5. So in the B, the size of the sample, so we have a sample. So in B, we have a sample of size 20, because we have 20 cars. Sample of size 20. Right, because we have 20 cars. In B, because we have 20 cars. Have 20 cars. Right, so this, in B, what we want is the probability that the mean load weight x bar of the 20 cars is less. Not just one single car. We are not talking about one car, but we are talking about 20 cars. Okay. All right, guys. I'm gonna probably stop here. I don't know if I'm gonna cover this. Solve this problem next Wednesday, because as I said, I need to cover at least one more section from chapter 8 on Wednesday, and yeah. So thank you for listening, and good night, everyone.
Professor.
Juliana, yeah, I see you have a message. Let me see the chat. I didn't see her. Yes. Who's talking? Juliana? Candy?
Yes.
Oh, Juliana. Okay. Yeah, Juliana. I'm listening. Go ahead. Oh yeah, I see you send me a message, right? Okay, work number 4. Yeah, I mean, we can meet. Can you send me an email? I mean, you can send me an email. So, to take an appointment and we can meet, I mean, this week, uh, I don't know, probably we can meet like a Wednesday or, before the class or Thursday. Um, it's up to you, but send me an email. Okay, send me an email. So then, we can find, a date or, I mean, a time. Probably it's gonna be like Wednesday or Thursday. We can meet Thursday or Wednesday. Okay, sure. Okay, so don't forget, just send me an email. All right.
Yes.
Okay. Thank you. All right, I'm gonna stop recording, I guess, and